Good day everyone. I am Usama, Research and Development Engineer at the Green Tech Institute. Today, I am excited to present the fruits of our research team work on a study on the classification of thermal defects in power transformers using transfer learning. With an introduction to the critical role of transformers and our objectives, then we discuss predictive maintenance and its importance. Next, we will cover the key defects in dry power transformers. We then examine various monitoring techniques with a focus on thermal imaging. Our dataset comprises thermal images, which we'll briefly discuss. We'll dive into the architecture of the convolutional neural network designed for this task and explore the concept of transfer learning. We'll critically analyze the results and finally wrap up with a conclusion and future prospects. We are excited to take you through this. Let's get started. Power transformers are critical in electrical grid, adjusting voltages for efficient electricity transmission. However, their failure can lead to extensive power outages and significant consequences. To mitigate this, our study focuses on predictive maintenance using deep learning models. We classify thermal defects in power transformers through thermal images. Early and accurate identification of these defects allows for timely maintenance, reducing risk, and ensuring grid reliability. So, predictive maintenance is a proactive approach that uses data analysis and monitoring to predict when equipment maintenance should be performed. For power transformers, this approach is vital as it enables us to avoid costly, unexpected failures by monitoring the condition of transformers and predicting when maintenance is needed. Organizations can schedule timely repairs, optimize resources, and minimize downtime. In our study, we utilize thermal images and deep learning models to predict potential defects in power transformers, empowering decision makers to take necessary actions before a failure occurs. Let's focus on the main defects that can occur in dry power transformers. These defects are critical to monitor as they can lead to transformer failures. Dry power transformers are susceptible to thermal overheating and partial discharges. Thermal overheating occurs when the transformer's temperature exceeds its safe operating limits, and it can be caused by various factors such as overloading. Partial discharges are localized electrical discharges that only partially bridge the insulation between conductors. These discharges can deteriorate transformer insulations and lead to breakdowns. Identifying and understanding these defects are essential for effective predictive maintenance. Several monitoring techniques that can be used to assess the health of a dry power transformer and detect potential defects. These techniques include partial discharge measurements. It is localized. The partial discharge is a localized breakdown of the insulation in power transformer. By measuring partial discharge, it is possible to detect defects in the power transformer insulation. There is also thermal images or thermal imaging. The technique is using a thermal camera to detect hotspots on the surface. There is the vibration analysis involves measuring the vibration in the transformer, the noise analysis emitted by transformer, and analyzing the data to detect potential issues. There is also ultrasonic testing and some visual inspections that can help to identify visible signs of damage or wear, and also the calculation of the overall health index. Now let's delve into some related work. There are several studies have have addressed power transformer maintenance using various approaches. For instance, one study employed an artificial neural network for defects classification with an accuracy about 94.76%. Another combined online and offline monitoring systems for predictive maintenance. There are also efforts utilizing the solid gas analysis for the oil immersed power transformer with machine learning algorithms like simple vector machine for classification. Additionally, some studies that have experiments with thermal imaging and deep learning for non-destructive defects detection. These previous work laid the foundation and context of our approach in this study. Focusing on the data set used in this study, it consists of about 255 thermal images of power transformer. These images are crucial detecting thermal defects in the transformers. The dataset is divided into three subsets. 70% of the images from the training set used the training the model. 20% are in the validation set for tuning, and the remaining 10% constitutes the test set for performance evaluation. By partitioning the dataset this way, we ensure a good balance between training the model effectively and evaluating its real-world performance accurately. For the architecture of the convolutional neural network, the CNN, developed from scratch, the CNN is a deep learning model that is ideal for image classification. Our CNN consists of 7 layers, including 2 convolutional layers, 2 polling layers, and 3 fully connected layers. The first convolutional layer uses 18 filters, size 5x5, followed by a max pooling layer. The second convolutional layer has 96 filters of size of 5 to 5. The fully connected layer consists of 120, 84, and 9 neurons respectively. This architecture helps in effectively recognizing patterns and features in the images. The trusted learning is when we utilize a pre-trained model and adapt it for a new related task. It's beneficial especially when the dataset is small. We essentially take a model that's already learned features from a large dataset and leverage those learnings. In our study, we removed the last layer and of the pre-trained model, freezing the weights of the remaining layers, forcing the model to use the generalized features. We experimented with 3 renowned models: the VGG16, Inception V3, and ResNet. We are going now to delve into the results and discussion. 4 models were evaluated: a custom-built convolutional network VGG16, Inception V3, and ResNet. Impressively, both the custom CNN and the ResNet has achieved 100% accuracy, making them the top performing models. The VGG16 followed with closely with 90.9%, and Inception V3 achieved 86.36%. The learning curves show that training loss and validation loss decreased and stabilized, indicating an optimal model fit. The high accuracy reflects the efficacy of the models in classifying thermal defects. It's noteworthy how transfer learning contributed significantly, especially considering that VGG16 and ResNet were originally trained and vastly different datasets, but adapted successfully for this specific task. As for future work, there is potential in exploring additional model, integrating sensor data, and possibly developing an ensemble method that combines the strengths of various models for even higher accuracy. These findings underscored the value of applying deep learning in predictive maintenance for power transformers. In conclusion, the importance of predictive maintenance in power transformer is evident. Through this study, we have explored how deep learning models can be employed to accurately classify thermal images, which is vital for the early detection of defects. Our custom-built CNN and the ResNet model notably achieved perfect accuracy. The success of transfer learning also highlights how we can leverage knowledge from large datasets to bolster performance even on a smaller dataset. These insights open the doors for enhancing reliability and efficiency in power transformers, which is critical for the stability of electrical grids. Looking ahead, integrating diverse data types and exploring more models that can push the boundaries even further are the references of our paper. And thank you all for your attention.